Okay, thank you. And certainly, I'm grateful to the organizers for inviting me to this seminar, especially to James. And the title was already announced. I'm going to talk about some recent results obtained in collaboration with several of my friends, which I will name in the course of the talk. So first, what the talk is about. As the title says, it will be quantum graphs, and especially I will be speaking about quantum graphs with a periodic structure, and what will be important about graphs with a non-trivial vertex coupling. So I think that most of you are quite knowledgeable about quantum graphs, but still maybe not everybody. So let me say a few introductory words to introduce the characters of this story. So the object of our interest are metric graphs, that is graphs which are with the edges, which are not just abstract objects, but something which can be identified with segments, with intervals. And the graph, as usual, is a collection of such edges and vertices connected in an appropriate way. Something like this. And on that graph, we will put differential operators. In general, say a Schrödinger operator. The Hilbert space will be just the orthogonal sum of the L2 spaces on each edges of the graph. And we consider a Schrödinger operator which will act on J's edge as simple one-dimensional Schrödinger operator. And of course, in most of the talk, I will be speaking of the simplest case where there is no vector potential and no scalar potential. That is, the operator is just the Laplacian or minus Laplacian. Now, about the vertex couplings, certainly if I have the operator defined by this differential expression, it is not enough to have it a self-adjoint. So I need to determine how the functions are coupled in the vertices of the graph. And since this is a second order operator, so I need the values of the functions and values of the derivatives. And then in order to have a self-adjoint operator in a vertex of the degree n, in general, I have to couple these two by the following linear relation, where U is an arbitrary unitary n by n matrix. This is, of course, a large family of self-adjoint operators, and I will be interested in some particle of them. One which is often studied is one which has the functions which are continuous at the vertices, which is a huge simplification because, as you see from this condition, the general condition depends on n square real parameters. If you require the continuity, this family is reduced to just a one parameter subfamily. So we have continuity in the vertex. And the sum of the derivatives is proportional to the common value of the vertex with some coefficients alpha, which is parameter specifying the particle self-adjoint operator. Alpha equals alpha is any real number. This coupling corresponds in this general form to the matrix, which is of that form where I is, as usual, the unit matrix, and J is a matrix which with all the entries equal to 1. The particle case of the delta coupling, of this coupling, where alpha is 0 when this sum vanishes, is called usually Kirchhoff coupling, and it's the simplest and in a sense most trivial. And the main topic of my talk concerns the couplings which are not Kirchhoff. Okay, so my topic is the spectra of quantum graphs, and that's something which is quite well studied. There is a lot of results about that. I can refer to the monograph of Dries Abercolaiko and Peter Buchman, for the information. But many of these results, or most of these results, I would say, concern the graphs with the Kirchhoff coupling. And as I said, I will consider coupling which is non-trivial, which is non-Kirchhoff. One introductory remark is that even if the operators we have here are Schrödinger operators, they differ in some aspects from the usual Schrödinger operators. For example, these Schrödinger operating graphs do not have the unique continuation property, which in particle means that you can have, for example, a compactly supported eigenfunctions. This is obvious, say, from the picture. If you take a graph which has a loop and the edges are rationally related, then you can have the solution which has zeros at the nodes of this graph, and therefore the rest of the graph simply does not know about such a solution. Okay, so now, as I said, I will be talking mostly about periodic graphs, periodic either in one direction or more directions. And in this case, of course, you can use the method common in the study of periodic system, that is Floquet decomposition. You take an elementary cell and decompose your operator into a direct integral over the dual cell, that is the Brillouin zone, as the physicists would say. And you study the spectra of this operator, which are typically discrete, and you look how they depend on this parameter theta, which is the quasi-momentum. From what I said about the unique continuation property, it's clear that the spectrum of such a periodic graph need not be absolutely continuous, again, in contrast to the usual Schrödinger operators. And I want to add that, in fact, the spectrum may not be absolutely continuous at all. And to illustrate this point, let me show quite a simple example of a magnetic quantum graph like that. It's just an array of rings which are coupled by at these vertices, and I have a magnetic field which is perpendicular to the plane of the graph. Now, the operator will be a magnetic Laplacian, that is the square of this this operator, where A is the magnetic vector potential. And the condition I assume are the magnetic delta coupling as introduced by Strikin and Schrader, which is practically the same as the delta coupling. That is, I assume the continuity at the vertices. And now the sum of these generalized derivatives is proportional to the common value. But in my particle example, because I have just vertices of degree 4, the magnetic part cancels and all reduces to the usual delta coupling. Now, in order to solve the spectral problem for these operators, I proceed as I said, that is, I take the elementary loop, which is just such a thing, and I take the solutions which which follow the standard ansatz, just the combination of the plane waves with a magnetic prefactor in each of these 4 links, and I couple them with the conditions here and here. That is, I couple them first in by the delta coupling at the point where the rings match, and I impose the Floquet conditions between these points here and here, which is an easy calculation. And what I get is the system of linear equations for the coefficients of these functions. And to make it solvable, I just have to look at the determinant, and it yields the spectral condition which looks as follows. That is, it's a quadratic equation with a discriminant of this form, and in order to get it solvable, I just have to have this thing, this function psi to be smaller or equal to 1, which means that the condition which I have is that this function eta must be smaller or equal than 4 cosine a pi. I forgot to say that the length of each ring is 2 pi. Now, this is something. This is something which, in the Kirchhoff case, get a trivial spectrum, and a non-trivial spectrum if the coupling constant is different from 0. The easiest thing to illustrate it is to show the graphical solution, which is on the next slide. Look, so this is the function eta. If you look back at the function eta, who knows the chronic-Penny model is basically the function, you know, from that. Just it differs by the factor 2 because there are 2 links of each ring. Now, if alpha is 0, then the function eta is just the cosine and hyperbolic cosine in the for negative energies, and you ask whether it is within this shaded area. So in the Kirchhoff case, you have the trivial spectrum; it's the whole positive real line and nothing in the negative one. Once you switch on the interaction one, once alpha is non-zero, then the picture changes. First of all, if alpha is negative, you have some negative spectrum because this function eta then extends in the shaded area here. If it's positive, it has only positive spectrum. But what is important is that you see that the function due to the second term of eta exceeds the shaded area, and you have open gaps, infinite number of them. Now that was for the non-magnetic case where A is 0. I recall that the width of the shaded strip is 4 cosine or 8 cosine 8 pi, which means that if the magnetic field, which is a constant, it's a homogeneous field, is half integer, then this cosine is 0, and all this strip shrinks to line, and suddenly you have the spectrum which is pure point. It consists of infinitely degenerate eigenvalues or flat bands, as a physicist would say. So that was an illustration. Just let me remark that even such a simple example can produce even much wilder spectra. For example, if you take, instead of a homogeneous field, a field which changes linearly along the array, and this slope of this change is irrational, then the spectrum of this operator is a Cantor set of Lebesgue measure 0. But that's not my topic. My topic is now about 2 questions, and the questions would be the following. First, I will ask whether the number of open gaps in the spectra of such periodic graphs is finite or infinite. And my second question would be whether the gap structure can depend on the graph topology. So let me start with the first question. First, a motivation. The finite or infinite number of gaps is the question which is certainly asked in for usual Schrödinger operators too, was asked at the very beginning of quantum theory. And we know that there is a dichotomy. Then if with the usual Schrödinger operator, if the dimension of the system is 1, you have generically infinite number of gaps, except some particle class which is well understood. If the dimension is 2 or more, then the number of gaps is finite, which is known as Bethe-Sommerfeld conjecture, formulated in 1930s, and something which is quite acceptable for physicists. Any physicist would accept it immediately. But mathematically, it proved quite hard problem. It took half a century. The first rigorous proof of the conjecture was given only in the 1980s. But by now, the problem is well understood. And I can refer to this Leonia Parnovsky review for the results. Now the question is how the situation looks with the finiteness of the number of gaps in quantum graphs, because quantum graphs is something which in a sense is mixing dimensionalities. If you look in Berkolaiko-Kuchman book, they say that the heuristic reasoning which gives the conjecture is applicable again, but they say that it is not a strict law. And the reason is that there is an effect of graph decoration, which was first observed by Eisenman and Schenker in combinatorial graphs, but extends to metric graphs. And it's like that. If you take a periodic graph and decorate it, that is, you glue to every vertex as the same finite graph, then you can produce an infinite number of open gaps. And so the situation where the number of gaps of such a periodic graph is infinite are quite frequent. So the question rather is whether the Bethe-Sommerfeld is a law at all, whether there are graphs, periodic graphs, which will have a finite number of open gaps. So from obvious reason, I would call such graphs Bethe-Sommerfeld graphs. Now, the answer would depend on the vertex coupling. I said that the general form of the vertex coupling looks like that. And another form of this condition is to decompose it into parts which would be called Dirichlet, Neumann, and Robin, which correspond to the eigenvalues of the matrix U, namely to the matrix to the eigenvalue -1, 1, and the rest. And of course, if you have the Dirichlet part or Neumann part, then one or the other parts here are absent. And such conditions, such couplings are called scale invariant, because the properties the spectral properties do not depend on the energy. If you scale the graph, you scale the spectrum. An example is, of course, the Kirchhoff coupling. Now, the first theorem here is that an infinite periodic graph does not belong to the Bethe-Sommerfeld class if the coupling at its vertices is scale invariant. So that's a negative result. And worse than that, we have a simple argument due to Rami Band and Grisha Berkolaiko, which says that generically the probability that an energy is in the band or in the gaps is different from 0 or 1, which means that generically you will have an infinite number of open gaps. So the question is, do Bethe-Sommerfeld graph exist? And my answer is affirmative. They do exist. And of course, since this is an existence result, it's enough to demonstrate an example. An example is here. Example is an old model revisited, quite simple graph in the form of a rectangular lattice. So we have an infinite lattice like that. And an elementary cell is a rectangle of the sides A and B. And to find the spectrum, you proceed as before. That is, you take an elementary cell like that. You impose the coupling here at the vertex. For me, it will be a delta coupling, and the Floquet condition between the neighboring cells. So it's an easy calculation, and it yields the spectral conditions or the gap conditions in the following form. So the positive energy k square belongs to a gap if this positive value of satisfies such a simple trigonometric condition. This is for alpha, the coupling parameter, positive. If it is negative, it looks similar, just tangent is replaced as cotangent. We leave out the Kirchhoff case because then the answer is trivial. The spectrum is always just a positive real half-line. Now, certainly, if alpha is negative, such an operator has a negative spectrum too, and can have a spectrum in the negative part. But for our question, it is irrelevant, because if it has a gap, the gap always extends to positive values. So it's enough to look into the positive gaps and to assess their number. So what is known from the old papers about this model? The spectrum depends on the ratio, number theoretical properties of the ratio of A and B, the sides of the rectangle. If the ratio is rational, it's obvious that the spectrum has an infinite number of gaps. If you look at these gap conditions, you see that if A and B are commensurate, then of course this function is periodic. So if it has a zero, which is then less than, it has infinite number of zeros. What is more interesting is that in the irrational case, the answer depends on the type of irrationality. Namely, if the ratio theta is irrational in irrational well-approximable rationals, which means that if you write theta as the continued fraction representation, then this sequence of the quotients is unbounded. Then the operator has again infinite number of open gaps. On the other hand, if theta is badly approximable, which is roughly Diophantine number, that is, if the rational approximants to theta satisfies this inequality with some positive constant c, then the operator may have no gaps at all. And in order to show you the simple situation, let me show the simplest example, somehow the worst, in some sense, the worst irrational, which is the golden mean. That's the continued in the continued fraction representation. You have just all ones. And then what you can say about this? So you have the following claim. So for the golden mean ratio, if alpha is absolutely large enough, that is either larger than this or negative smaller than minus this value, then the spectrum has infinitely many open gaps. Then if alpha is within this interval, that is smaller or equal to this n, and larger than this negative quantity, the spectrum has no gaps. But now comes the point, if alpha is between this quantity here and minus pi square over square root of 5a, then the spectrum has non-zero and finite number of gaps, which means that that's the result we were looking for. The corollary is that Bethe-Sommerfeld graphs exist. And in fact, you can say more. You can say that the window when this happens is quite narrow. It's just 2% of the whole interval where the effect can take place. But you can do even better. you can find the sub-intervals of this interval when the operator has exactly n prescribed number of n gaps. And these are these inequalities. That's the sequence of numbers which are all less than this critical value. It's an increasing sequence. And between the subsequence aj and aj plus 1, there is you have j open gaps. Okay, so that was an example. Of course, this is not the only result. You can formulate the result in more general terms. Here is a theorem. If you have in this model the ratio theta, and for the theta you define gamma plus and gamma minus such quantities, that's the minimum of infimum, such combination where this is floor function, and then you define gamma minus where you replace when you replace the floor function by the ceiling function and tangent by minus tangent, and then you compare these things to the quantity which is known in the number theory as Markov constant. That's the infimum of all the constant for which this inequality has infinite number of the pairs PQ. And if there is a gap between these quantities and this quantity here, then the operator has a finite and non-zero number of gaps, which allows you to construct further examples. For example, you might think that in the example you had just negative numbers of alpha which produce. With this theorem, you can produce examples where the same happens for positive values of alpha, etc., etc. And you can generalize these things. For example, you can take it to higher dimensions. There is this paper by Andrei Turek. It shows that this similar effect can be found for lattices in 3 dimensions, etc., etc. Okay, so that was my first question. To introduce my second question, that is about the dependence of the cap structure on topology, I need a small introduction. Namely, I told you that you have a lot of possible admissible vertex couplings, but one certainly asks what's the meaning of these couplings. So one old and natural idea would be, okay, you have too many parameters, and since you want to model something which is in physics, it's a system of wires, in fact, tubes which are thin but of a non-zero diameter. Let's take a system of tubes and shrink the width to 0, and look what happens in the limit. So it's quite a natural, a simple idea, but as usual, making it a mathematical theory is quite hard. You can prove that if you do it with a Laplacian in this thin tubes, Neumann Laplacian, and you shrink the tubes width to 0, you get a graph with a Kirchhoff coupling. And if you are interested in other couplings, then you have to do a lot of exercises. You should add potentials which scale properly. You should add magnetic fields. You have to change the topology. You can finally produce a system system of tubes which produce any coupling. But it's a rather baroque construction, and it's not of much practical use. So the other approach is pragmatic. Forget about a general answer to the question about approximating all the couplings, and let's ask whether the particle coupling will suit to a particle physical model. And one model which inspired what I'm going to tell you now came from consideration about the Hall effect. Now, Hall effect is something which is nowadays well known. You take a sample, you have a magnetic field, you let the current, and you measure voltage perpendicular to the direction of the current. But and the mechanism of that effect is well known. It earned 2 Nobel Prizes. But there is also something which is called anomalous Hall effect. The same thing happened, but without the magnetic field. And that's something which is much less understood, the mechanism of the thing. And there was a recent attempt to model this anomalous Hall effect using quantum graphs. That is taking such a system of rings, which topologically is again a square lattice, and looking in the strip composed of looking for transfer properties. So that's the paper here. But the model has a flaw, and I think you see it, because you see I hope you see my screen. You see that in this picture which I took from this paper, you see arrows. So the authors of the models, my good friends, by the way, they had to impose by hand the assumption that the electrons are running in particle direction. Of course, this is something you cannot justify from the first principles, because you cannot tell a particle on the line go left or go right. So this is a flaw of the model. But thinking about that, we realized that you cannot do that in the rings of the model, but certainly you can do that in the vertices. You can impose the condition in the vertices which violates time reversal invariance. And in order to find an example of such a coupling, let me recall how the on-shell S matrix looks for the couplings specified by the unitary matrix U. It looks like as follows. So in particle, if k is the momentum is 1, the U is just the S matrix. So it inspires you to consider coupling which where the violation of the time reversal is in a sense maxima. So you take the matrix U which switches the directions, go from the first to the second to the third, etc. This matrix U, and if you put this matrix U, you get the conditions which in components looks as follows, and you see immediately that it's non-invariant with respect to the time reversal, which in quantum mechanics is represented by complex conjugation, because if you complex conjugate, this does not change, but this part changes sign. So let us look now how the properties of this coupling look like. First, take the simple thing, a star graph where you have just one vertex with this coupling here, and n half lines connected by this coupling. So it is easy to see that it has always a discrete spectrum. So the positive spectrum is essential spectrum is the positive half line. That's easy. But it is a negative spectrum, a discrete spectrum for all n which are at least 3. 2 is trivial. And the number of eigenvalues there goes from 1 to the integer part of half, especially for 3 and 4, just one eigenvalue equal to -3 and -1. In general, the eigenvalues are given by this formula. It's minus kappa square, where kappa is this thing here. Okay, now the on-shell S matrix for this U is something which is given by the formula I've shown you. And it would seem that this, if you go with the energy to 0 and to infinity, then the limit of the S matrix is -1 and 1 respectively. But this is a formal argument which may be wrong, because recall that the matrix U can have the eigenvalue -1 or 1, which of course spoil this limit. And one example is if you take, say, a Kirchhoff coupling, then the S matrix is independent of the energy indefinitely. It's not a multiple of the unit matrix. So in order to see what happens here, you can take the matrix U I showed you and calculate the elements of the S matrix. For convenience, I introduce this variable eta, which is in terms of the momentum this thing. So for example, the limit k equal to infinity is eta going to -1. And you have this formula. Now you will not see without analyzing it, but you can look into what happens, say, for n equals 3 and 4, and you have these expressions, and I will see clearly that there is a big difference in the limit when the energy goes to infinity, that is eta goes to -1, namely that for eta for n equals 3, and in general for any odd value of n, the limit is indeed 1, while for n equals 4, and in general for any even n, the limit is not equal to 1. And the reason is that for odd values of n, the eigenvalue -1 of the matrix U is missing, and that has a consequences, because it means that for odd parity of the vertex at high energies, the S matrix is 1, and there is almost full reflection, while for even it is not the case. And in order to see how it shows this effect in periodic graphs, let me now compare two lattices. One would be a rectangular lattice with this coupling here, and the other would be a hexagonal, or as people say, honeycomb lattice. So the elementary cell here is this cross. Here it is this graph here. So there is one vertex in the elementary cell of this lattice, two vertices, and you produce the spectral conditions as before, that is imposing the coupling in the vertices, imposing the flaw conditions here, here, and here, and here, and here. So it's again an easy computation, and the result is the spectral conditions are here. So again, they look complicated, and just looking at the formula at a glance, you will not see much, except that there will be something, these infinitely degenerate eigenvalues, what I call Dirichlet, but here you would rather say Neumann eigenvalues, because both contain this sinus scale A. So if this is a multiple of pi, certainly this condition is satisfied. But now, in order to see the difference, again, the good thing is to look at the graphical solution of these two conditions. So it is here for the rectangular lattice and for the honeycomb lattice. So first, there are some. So again, the solution is you have a curve which is cosine and hyperbolic cosine, with a slope which depends on the value of L, the length of the edges, and the spectrum is there where these curves cross this shaded area. And you see that there are some common features. For example, there is always a negative spectrum. There is one band for the rectangular lattice, two bands in the negative part for the honeycomb lattice. If the lattice is huge, I mean the length of the length L is large, then the bands will be narrow around the values -1 and -3. That is the eigenvalues of this star graph. Secondly, there is always an infinite number of gaps. And you see that sometimes it may happen that that a gap will degenerate to a point when this cosine crosses this point for particle L. But there is one huge difference. If you look at that, you see that for the rectangle lattice, if the energy grows, then the bands occupy more and more room here. That the bands on the K scale, on the momentum scale, will become more and more narrow. If you transform it into energy scale, that is, you take the K scale, then the gaps will be asymptotically of the constant width. In contrast, here you see that the shaded area looks completely different. And in the honeycomb case, that's the gaps which dominate the spectrum at high energies. And the reason of the difference is clear. Here, the parity of the vertex is 4, which means that the high energies the particle has coming to the vertex almost the same probability to go all 4 directions. While in the honeycomb lattice with degree 3, you see that particle at high energies, particle coming to the vertex is almost surely reflected. That is, it stays confined. This high probability stay confined within a single edge. Okay, so this is you can play with that. You can take not only this coupling. You can, for example, take an interpolation between this coupling and the delta coupling, which is given. I will not give you the formula. Just it's the interpolation which goes for the parameter between 1 and 0 goes between delta and this thing. And you can produce interesting comparison. For example, if the delta is taken in the Kirchhoff case alpha, you see that for the here in the delta case, you have the spectrum which is a positive line, nothing in the negative. Here the spectrum you had before, and now there is always a negative spectrum. So the question is, what will happen if the parameter goes to the delta coupling? There is one band which escapes to minus infinity. If you take alpha, which is non-zero, you can further interesting effects. For example, that the dependence on the interpolating parameter is not smooth. You see here that these curves which show the gap boundaries or band boundaries, they're not smooth. They have angles. But enough of that. Just a couple more examples. You can see the effect, the dependence on the vertex parity, also in finite graphs. There, of course, the spectrum is discrete, but let me show you the following example. You take graphs which has a finite symmetry, namely the graphs which are at the edges of the Platonic solids, 5 Platonic solids, and you impose our rotating vertex coupling at all the vertices, and then you ask what the spectrum is. I will not formulate it as a theorem, but I will show you in words what happens. So for 4 of them, that is the tetrahedron, cube, icosahedron, a dodecahedron, you have at high energies the eigenvalues which are multiples of squares of multiples of pi with the with the error of OK minus 1. That is, the eigenvalues asymptotically are just asymptotics of the Laplacian on a single edge. If you take an octahedron, then you have 2 additional series, namely those with k like that. And like that, you see that they differ from integer multiples of pi, again with some error which vanishes at the high energy limit. And the reason is again clear. All these 4 have even number 3 or 5, while octahedron is the only one of among them which has the vertices of degree 4. And if you compare, if you take the same thing, but you replace this rotating coupling by the delta coupling, you see no such difference between these cases. Couple more examples. So James, 15 minutes, but we start, please. Do I have a couple more minutes? Yeah. Okay. Two more examples. So one would be the following. I take again a very simple graph, which first would be an array of rings, and I put my my rotating coupling at these vertices. So then, if they touch, the spectrum is almost trivial. The spectrum is just the positive half line, in which you have embedded eigenvalues at positive integers. Of course, the scale is the same as before. The length of the ring is 2 pi, and in addition, I have an infinitely degenerate eigenvalues at -1. Now let me look what happens if I, instead of the close connection here, I take a loose connection. I couple these points with a connecting link of some positive length, like that. So then the spectrum becomes much more interesting. Namely, for any positive L, I see that first, there are again the infinitely degenerate eigenvalues. Any non-negative integer produces an eigenvalue of infinite multiplicity. Secondly, a way of this integer spectrum is absolutely continuous and has a band and gap structure. In the negative part, it has at most 2 gaps. There is nothing between -1 and 0. And in this interval, there is one or two gaps, bands. Sorry, there is a single band when the length is pi. That is half of the length of the perimeter of the ring, and otherwise there are two bands. But what is the most interesting thing is that the spectrum has infinitely many gaps, and this quantity, look at this quantity. This is a quantity which was introduced, I mentioned it already, the result of Rami Band and Grisha Berkolaiko about the probability of being in the spectrum. So what this means is you take the measure of the spectrum in the interval from 0 to k, normalize by k, and take the limit where k goes to infinity. So this is a meaning of the probability of finding the energy value or the momentum value in the spectrum. And in this case, the probability is 0. So if you know, so that's what I just said about the probability. So recall that if L was 0, if there was no connection links, the positive spectrum was a whole positive half line. So certainly the probability of being in the spectrum was 1. If the connecting links are there, this L is positive, the probability is 0. And you can combine it with the recent result by Grisha with Latushkin and Sukhtaev. They proved that under some conditions which are satisfied here, the spectrum, if a link of the graph shrinks to 0, the spectra converge to each other. So the spectrum of the case of the graph with connecting links converges to that with the tight coupling. And now the probability is 0 whenever L is positive, and it's 1 then. So it shows that the limit exists. It holds, but it is rather non-uniform. And okay, one last example. Now let me say something about the transport properties. Again, how the parity shows. So let me compare two guides, graph guides. You take a strip of cut off the graph. On the one hand, you take a graph which is cut off of the rectangular lattice like that, and on the other hand, you take a lattice which I would call a brick lattice of that type. Now I would guess, if I remember what I said about the motion of a particle through such a graph, that in this case the particle would move at high energies freely, or the bulk of the graph, because there the all the vertex parties are 4 even, but on the edges of the strip the parity is 3. So you'd expect that there would be no transport, or that the transport would be suppressed there. On the other hand, for this example, you would have at this edge, there you have vertices of degree 4. So we'd expect that the transport is possible, while all the other vertices inside in the bulk has degree 3 or 5. So you expect that the transport would be suppressed in the bulk. And well, now in order to look whether this can be true, you take, well, here you have Floquet analysis. You take one layer of such a graph and calculate the eigenfunction or generalized eigenfunctions corresponding to a given quasi-momentum, taking the standard ansatz, and you compare the size of the generalized eigenfunction if you normalize the eigenfunction in one layer of the graph to 1. What happens with the coefficients? And here is what you see. So in the first case, in the lattice cut of the rectangle lattice, then you have to leave out the points which are close to this infinitely degenerate eigenvalues. So you leave out small intervals around these points, and in the rest, you see that the eigenfunctions on the edge of the strip at high energies are suppressed as O of keta minus 1 as k goes to infinity. So that's the rectangular lattice, and as expected, there is no transport on the edges of the strip. On the other hand, if you take the brick lattice, and again you avoid the vicinity of the infinitely degenerate eigenvalues, and you look at the coefficients, you see that the amplitudes of the functions decay away of the edge. That is, the farther you go to the bulk, so more is the transport suppressed. And again, it confirms our expectation, that is the even parity of the vertex with this coupling favors transport by the odd parity transported. And my last remark is that a warning, that is, even if it looks like that, this example of the brick lattice, this example where the transport goes along the edge and nothing in the, or very little in the bulk, it is not a topological insulator, even it looks like. Because the big difference is that in the topological insulator, the direction of the motion is topologically protected. You can go only one way. While here, if you look at the dependence on the quasi-momentum, you see that if your quasi-momentum goes through the Brillouin zone, your particle goes along the edge, but it can go this way or that way. Okay, so I think I used my time. So what is remaining is to say thank you for your attention.